Okay, looks like we have stabilized number of participants here. So why don't we get started? So welcome everyone to our new seminar series and optimal energy optimization and learning, which is a seminar series at the interface of energy optimization and machine learning. And we are organizing this from MIT with my colleagues Vladimir Dvorkin and Stefanos Karaolo. And in the past, we have done energy system seminars on campus, primarily for an on-campus audience. This time we figured out we wanted to try something new, given that there are not that many people on campus yet. And also that I think these topics, so energy optimization and learning, is of an interest to a wide audience out there. So the idea is to invite speakers like the one we have today to discuss the latest developments in the theory and applications of optimization and machine learning in modern energy systems. And we do have a great lineup of speakers, as you can see on our intro slide here. So this is the first session in the series, and we will do this every second week. We have 4 speakers lined up for now. Maybe we'll add some more. Let's see. And it's always at the same time, 11 a.m. Eastern on Fridays. That way we can capture most of the time zones in the US and also perhaps the tail end of the day in Europe. So there's a website, as you can see there, with information about the talks, and also where you can sign up for a Google email list, as well as watch previous talks. So we want to make this an interactive type of seminar series. So we encourage you to ask questions also along the way, as well as at the end of the presentation. You can ask questions by using the chat box, but also feel free to speak up and ask questions directly. In that case, you may want to use the raise hand feature in Zoom, or you can also turn on your camera. And thank you very much to the main organizers, Vladimir and Stefanos, for really making this happen. So with that, I'll introduce today's speaker, and we are very excited to have Professor Vassilis Kekatos from Virginia Tech joining us today. Vassilis is an assistant professor in the ECE department at Virginia Tech. He did his PhD at the University of Patras in Greece in 2007, and he has received multiple awards, including the National Science Foundation Career Award and the Marie Curie Fellowship Award. He has been at multiple institutions in the US, including University of Minnesota, University of Texas, Austin, as well as Ohio State University. He is on the editorial board of the IEEE Transactions on Smart Grid, and his research focus is on optimization and learning for future energy systems. So I think we can say it's a perfect fit to open our seminar series here. With that, let's turn it over to Vassilis.
Thank you very much. Thank you very much, Odin, for the introduction. Let me share this. And also, I would like to thank all 3 of you with Vlad and Stefanos for inviting me, and also for giving me the opportunity to start this seminar. And I'm very glad and excited to present our work on deep learning for solving the optimal power flow here at Virginia Tech. And here, what I would like to present here is a couple of works that we have done on how we can accelerate and how we can expedite solutions of the optimal power flow, or OPF. And we don't just want to use OPF as a black box. We would like to use and incorporate any physics or any specifications, any inside information that we have, so that we can improve off-the-shelf tools and we can make them even better. So I would also like to acknowledge the support from NSF and Nextera Analytics for supporting this, for funding these 2 works. So our motivation is that distribution and transmission grids alike are going through transformational changes, And I guess I don't have to say much that solar and in general renewable generation and distribution grids creates fluctuations, and we have more and increased needs for a more frequent decision making. And so, for example, here you can see on a feeder, I have plotted the total solar generation throughout the day. And this is the total load throughout the day as well. And you can see the large fluctuations of solar can create large and abrupt voltage excursions on the right-hand side. So on this plot, I have, again, time of the day aligned with this. And on the vertical axis, I have voltage deviation from the nominal voltage. And the different curves that you see are different buses. So you see that there are pretty abrupt voltage excursions, and traditional equipment used by utilities, such as regulators or capacitor banks, may not be able to handle that. And on the other hand, we know that if we use the smart inverters interfacing different smart grid technologies or different distributed energy resources, DERs, such as solar, batteries, electric vehicles, they can help us by reactive power support so that we can control these voltages. However, the key question here is, how do you coordinate these DERs on a very fast scale and also in a scalable way, right? So if these fluctuations are happening within every minute or so, then we have to be pretty fast and keep, catching up with the changing conditions of the grid. So that's on the distribution side. How about the transmission side? On the transmission side, we have some similar observations that ISOs, independent system operators, need to solve increasingly complex optimal power flows and versions of the optimal power flow. We may have more participants, right? We may have like virtual power plants, we may have aggregators that come and have to be dispatched at a finer time scale. Why finer time scale? Again, because of renewables. And not only that, but now we may have to do security constrained versions. We may have to take into account stochasticity, so we may have different scenarios. And we may also have to take into account binary variables and unit commitment decisions that have to be changed more frequently. And also all these operators, they get like larger and larger footprints, like MISO started up here in the Midwest and now has expanded all the way south. And perhaps ISOs may be merging, or at least we may envision some coordination between the ISOs, which means that, for example, if somebody can fix or somebody can optimize the flows on the tie lines between markets, then each market can somehow solve the problem in a decomposed, localized manner. So we have all these challenges on the OPF, and let's see where we are right now. We have quite few advances in numerical optimization for the optimal power flow. We have convex relaxations. We know that we can do successive linearization. That was the good old, bread and butter of OPF, non-linear OPF. But now that comes into different flavors, such as real-time OPF, where you solve things in a dynamic fashion. We have distributed solutions where you have areas, as I said, for example, like the ISO, where they coordinate, right? And they have some coupling variables, which may be few, right? And if you fix those variables, primal or dual variables, you may be able to accelerate these solvers. And then we have also all these advances in mixed integer solvers. So for example, they allow you to do lazy constraints, which means that you don't have to include all the flow constraints, for example, but you can increase them successively. Or you can do warm starts by providing some first guesses of continuous or binary variables. So all these advances in optimization and numerical algorithms are great, and we are trying not to avoid them, not to bypass them, but to kind of like assist them and support them by using learning. So how can learning help numerical solvers? It can help them in many different ways. So let's say we have the grid conditions, right? Let's say the current solar or the current wind generation, or let's say the low demands happening right now on a distribution feeder or at the transmission network. And let's say we feed those through a deep neural network, we call it DNN, or any other machine learning model. Here we will focus on DNNs. And the output of this model can be any of this. So it can be, people have been thinking, okay, this DNN can be predicting the set points of smart inverters. It can give us warm starts, such as Kari Baker, that will be presenting in a couple of weeks, has proposed. Or we can use this DNN perhaps to linearize a real-time OPF, right? We can also use it, people have advocated using DNN for finding which constraints are binding, meaning which of the inequality constraints become active. If I know those a priori, then I can drop all the other constraints that will not be binding, because at the end they will not affect the solution. And I can have a OPF with much fewer constraints. That can significantly speed up the OPF solver. Or I can predict commitment decisions, or when we go to decentralized solutions or distributed solutions, one can say, I will have the DNN, not finding the whole OPF setup, but predicting some key coupling variables, like the tie lines, right? Or perhaps some dual variables that will allow me to do dual decomposition in much faster, because I will have these variables warm started. So all these ways are things that DNNs can help. And also to kind of like cover more ground on the existing literature, we know that people have, there is a great concern on feasibility. Do these decisions provided by DNNs, are they feasible? It's very hard to enforce feasibility. So people have been using different tricks with KKT conditions, Karuskun-Tucker conditions of optimality, or people have been using MILP solvers so that they can verify the safety of DNNs. And also people have looked into improving DNNs by using some physics of the problem. For example, by regularizing the DNN, so it's not an abstract representation, a generic representation, but it can be an input convex DNN. Or they have been thinking of unrolling iterative algorithms and having a DNN with its different layers mimicking the iterations of an algorithm. Or they have been inspired by the graph structure of the OPF, since it's operating over a grid graph, and they're trying to bring some graph structure into the DNN as well. Our open questions here in this presentation would be mainly two. Here I have a third one, but that one I think we'll not have time to cover. So let's say we have the general setup. So we have the DNN, we input some grid conditions, and we would like to get the OPF solutions. That will be the general setup that we will be considering. And we were thinking, how can we make these physics informed? And to do that, you can see the three components. And you can think, first of all, of these solutions, right? So these are the labels, what we call in machine learning labels, right? It's like what the learning model should be targeting, should be mimicking. So these labels in machine learning are generic. They're like images, right, of traffic lights or images of elephants or whatnot. Here, these labels are specific. They may have some structure, right? Because these data are the outputs of an optimization problem. Then when we go to the DNN itself, it has some structure and it has some architecture, I should say. And people have tried to impose some structure. But what if here you have to impose some communication constraints? And then the third question is regarding the grid conditions. When we solve the OPF so far, we have assumed that we know perfectly all the uncertainties, right? We know the solar, we know the demand, and we solve the OPF. Can you solve an OPF without knowing exactly these inputs? I don't think so. We cannot solve it, right? An OPF says, give me these parameters, I'll give you the optimal primal points. Can we solve an OPF without knowing exactly what's happening in the grid? So that will be our third question. So here we will handle first the first question and then the third question, and we will slightly touch upon question number 2. And we have two parts, what I call OPF-then-learn, the first part, and then OPF-and-learn. And let's see how they are different. Starting with the OPF-then-learn. So let's say let's see like one application, which is to find the set points of DERs. And how do we solve that problem? We can solve it through an OPF. So I have some optimization variables X, let's call them X. This can be, for example, the reactive power set points of the inverters. And this problem depends on some parameters theta, which we discussed earlier. This can be the active reactive loads or the solar. There is also some topology here and line impedances and all that. And we assume that those are captured in the F and G and they remain fixed for the time being. So function F can be, for example, we would like the objective, let's say our objective is to minimize the losses on the lines. And let's say our constraints are to ensure that voltages are within limits and inverters satisfy apparent power constraints and lines are okay in terms of ratings and transformers. So we have this problem to solve where it's a parametric problem in over the variable x, which is the minimizer here, x sub theta, but also depends on the parameter theta. So we have a parametric optimization to solve. And every time the utility collects the data theta, solves the problem, and dispatches the set points q to the inverters based on x theta. Instead of having these being solved repeatedly, which may take some time, especially when you want to solve this in real time, let's have a DNN to accelerate, trying to find the minimizers of this problem, so that we can accelerate the solution of this, right? So this idea is what people have called, have termed learning to optimize. So it's not the general machine learning context, is the particular example where you are trying to learning how to optimize. So the key idea is to have a deep neural network that, given the grid conditions, you are trying to find some predictor, x hat, of the set points, or of the, in general, of the optimizer, x theta. And the DNN is parameterized through some weights W that you need to find. How do we find these weights? This is usually done in 2 steps. And the first step is that you have to solve many, many different OPFs, many different thetas, and you will find the minimizers x theta. Let's say you have to solve capital T of this. Then you created your data set, you put it on the side, and now you have to go and do step 2, which is to find the weights of the DNN. In other words, train the DNN. How do you do that? One way to do it is to minimize the mean square error, MSE, between the output of the DNN, x hat, with respect and minus the actual minimizer, right? So this is the predictor, and this is the labels that we are after. Okay, so now this is the L2 norm squared, and it's summed up over all the scenarios and instances of the OPF that we had. And we claim that this process treats the OPF as a black box, right? It doesn't see any properties of the x theta. It just says, okay, give me theta and x theta, and I will do my good old training of deep neural networks using standard data fitting functions. And not only that, we should say now that this process can be time consuming because you have to solve this step 1. So you have to solve many, many OPFs, right? And now when the topology of the feeder changes, then you have to redo the DNN. You have to retrain it, which means that you have to solve step 1 again from scratch multiple times. So how can we save on this, and how can we make this process more data efficient? How can we make it, how can we train the DNN in a faster way so we don't need so many samples? And our proposition to this is to what we call sensitivity-informed training. What is that? So let's step back a bit, and I would like to claim that the previous training process is a bit wasteful. It treats, as we said, the OPF as a black box. Give me theta, given theta, grid conditions, give me the minimizer, right? But it doesn't see that the OPF as a machine, as a module, as a piece of software, it gives you a bunch of other things that they are pretty useful. And sometimes this other side information, you already have it, and perhaps you're not using it. So the OPF solvers usually usually give you the dual variables of the problem as well. You also know the form of the functions f and g, the objective and the constraints. You know what they look like. And you also know that the primal and dual points have to satisfy KKT conditions, optimality conditions. So how can we incorporate all this side information that is sitting there idle? We can do it by doing what we call a gray box optimization, where now we, or training, I should say, where we train the DNN to match not only the minimizer itself, but also to match its sensitivity with respect to theta. So let's see this idea in a bit more detail. So we have that the minimizers is a vector, and it's a function of another vector theta. So let's say we are able to compute the partial derivatives of x with respect to theta. So that will give us a Jacobian matrix, which we put here. And let's say that magically somebody gives you these sensitivities. It says, hey, the minimizers like change with theta in this particular way. Then it would be nice if we can ask the DNN to have exactly the same sensitivities. Not exactly the same, to fit, to match, to try to imitate the same sensitivities. So this other Jacobian, the first Jacobian matrix here, is the Jacobian of the output of the neural network with respect to theta again. And remember, this theta is the input to the DNN, not the weights. Usually when we train a deep neural network, we care about the gradients of the output of the neural net with respect to the weights, because we are training it. Here, we also want the derivatives with respect to the inputs of the neural network. This is what we call sensitivity-informed deep neural network. And this rho is some parameter that can be fixed, trying to adjust, balance the two parts, the two terms. So now, when we pose this problem, we have to deal with two questions. One question is how to deal with the Jacobian of the DNN. Can we compute this? And the answer is yes, surprisingly. It's very interesting, but all these training software and platforms that are out there, such as TensorFlow, they have automatic tools that they do the so-called automatic differentiation. So you can easily capture, you can easily compute the sensitivities of the neural network with respect to the input. And what is surprising to me is that not only we can capture it here as a function, but also we can compute the derivatives of this Jacobian with respect to W now. Because when you're optimizing the DNN, you will also need those gradients as well. So nothing to contribute here. This is already there. We didn't do anything. We just used it. But I would just... Yeah.
Vassilis, there's a question for you from Dalal. Why do we use F norm is the question.
Yeah, so here the Frobenius norm. So we just pick some norm that captures matrices, because this is a Jacobian matrix and this is another Jacobian matrix. So we are comparing matrices. So the Frobenius norm is kind of like entry-wise L2 norm of if you vectorize the two matrices. This, I guess, it's more amenable to like optimization of the DNN and using standard tools of optimization. I agree that one could say I could optimize the maximum singular value or something like that, or the maximum row sum. That may complicate the process. We didn't think about it, but I guess this was the natural thing to make the optimization easier.
Thank you.
And yeah, in fact, I'm not sure if TensorFlow can handle other norms, but for sure the Frobenius norm, because you can see it as an entry-wise version of this, it can be handled. Now, the second question is, okay, if we have this done and we didn't do anything about it, I just want to put it up there. The second question is, how do you find the Jacobian of the OPF minimizer? And for that, we will do sensitivity analysis. And we have many great results in that area, and many from the audience, I'm sure, have worked on this area. Before going into the math of sensitivity analysis and how it is applied to the OPF, let me give you a small toy example so that perhaps it whets our appetite. So let's say we have the PJM 5-bus example, this one, a transmission network toy example, and we want to solve the AC-OPF, and we changed the loads from at buses 2 and 4 at different values, and we want to dispatch generators 1 and 5 at buses 1 and 5. And here are the optimal solutions that we get. So this is the optimal solution of P5, so the generation at bus 5, the active generation with respect to the P2 and P4, which are the loads, everything is in per unit. And you see we get this shape, this interesting shape, which is kind of like a kite, where it's flat here and then the tail of the kite kind of like flaps down. Okay, so we created 20 points, optimal like OPF points, and you can see them here in the circles. And we used exactly the same points to train the plain DNN and a sensitivity-informed DNN. And we used the same training data. We used the same architecture. The architecture was optimized for the PDNN, so to give it the full advantage. And then we used the same optimizers, and we optimized the parameters of the optimizers, such as learning rate and so on, so that we get the best for each one of the DNNs. We used the same architecture for SI, but it was optimized, as I said, for PDNN. And this is what we get. This is the fitting that we get. Here you see that the sensitivity-informed DNN does get a kind of like flat kite, and the tail does flap down when we go to higher loads. Whereas this guy gets a kite which is kind of like bented a bit. There is a bend, and also there is no tail. It failed to capture the tail, where here the gradients were very steep, but PDNN didn't know it. And SI-DNN kind of fixed that problem. So this is kind of like what we are dealing with, and I'm just presenting these two examples so that we can see it visually, because from later on we'll just see numbers and we may not get the main idea. So going back to our, now going to the math, let's try to do sensitivity analysis, and let's start from the easy case, which is DC-OPF. So let's say, going back to distribution systems, inverter control, let's say we use the linearized distribution flow model. In that case, the OPF you have to solve for dispatching inverters looks like a QP. It takes the form of a quadratic program. Here we have X is the variable, theta is the parameters, and the parameters appear linearly in the objective and the constraints. So this is a multi-parametric quadratic program. And the good news for us is that MPQPs have featured many nice, neat properties. One of those properties is that you can take the space of thetas and you can partition it into polytopes, which are described by inequalities, linear inequalities like this. And within each one of these critical regions, we know, surprisingly, not surprisingly, but it's interesting that the X within that region is given is an affine function of the theta. So let's say I solve for one theta that falls into this region. I can compute the region. I can compute the NK and TK describing the green area. How can I compute it? I don't have those derivations, but they depend on the parameters of the problem and which constraints got activated. That's the key ingredient. So for all those thetas now, I know that the X is given as an affine function of theta. And again, the matrices L, R, and T can be found in closed form very easily. I go to the red region, things change a bit, but I will have a different L and R. So what is the bottom line of this? The good news is that if you are looking for the Jacobian of X with respect to theta, then that's right in front of us is just LK. We got it very easily. Some results on this. We trained the DNN to operate between 10 a.m. and midnight. And here we have training scenarios, which is a percentage of the total number of scenarios. And here I show the mean square error and the computational time only for step number 2. not for step number 1, for step number 2, which is the training of the DNN. We have the plain and the sensitivity-informed DNN. And of course, when we use more training, the MSE decreases. But I would say for the SI-DNN, it decreases more gracefully. And you can see for 20% of the 20% of scenarios, the MSE of the PDNN is 220, say. This is 120, much smaller, for only 1/4 of the data. I should say that these MSEs, of course, are computed on the testing data, and they are averaged over 100 Monte Carlo runs where we randomize the training scenarios. How about training time? Perhaps by including all these derivatives and all these Jacobians and all the, the Frobenius norm and matching matrices, things may go bad in terms of like training time. You see that the training time does increase, but not so, I would say bad. So why is this good performance? We can attribute it to the fact that the SI-DNN now learns to match not only the minimizer at every point, but it also learns to do a linearization around that point and match all the other points, a cloud of points around each training datum. So in this way, essentially, we are artificially increasing the data that we have to train the DNN. So we improve on data efficiency. We have to solve fewer OPFs for step number 1. Or if you give me more OPFs because you already have them, I can do much better in terms of mean square error. So now, how do we do? Let me check on time. So we start, let's say around 10. So we are 25. Okay. So now, how do we do? How do we do in terms of the AC-OPF? This was DC-OPF. Things were easy, right? We had MPP, multi-parametric programming. Things were easy. How about the AC-OPF? Here we can do sensitivity analysis for the OPF and see what we can get out of that. We know that when you use a non-convex solver to solve the OPF, then the optimal, which may be locally optimal now, primal and dual points satisfy the optimality conditions. So we have the objective and the constraints, assign some Lagrange multipliers, and this is the Lagrangian function f plus lambda times g, right? And we take the gradient of that with respect to x, set it to 0. We have complementary slackness, g times lambda should be 0, g is primal feasible, and lambda is dual feasible. Okay, so these are the conditions that the x, lambda, and theta should satisfy. Now, what we would like to do is that we would like to perturb we would like to see how the solution of this problem changes when theta changes by infinitesimal change, d theta. In that case, we will get to a new point, feasible point, which is the x dx lambda d lambda, and we would like to find this point. For this point to be optimal, the equivalent conditions have to be satisfied. And how do we ensure that? We do a first-order Taylor series expansion, and we ensure that that expansion, like the conditions hold even for that expansion, for the new point. So for that, we will compute the total differential of the two equality constraints. I skip the first one because it's a bit messy. Let's go for the second one, which is a bit easier to see. Let's say here we have a product rule, and we will compute lambda times the differential of g. But this is the total differential, so it's del g with respect to x times dx plus del g with respect to theta, d theta. And then the product rule says that I will also have g times d lambda. That should be equal to 0. I do the same for the first equation, and I get some conditions, right? And now these conditions give me equations that I have to satisfy, that have to be satisfied for the dx, the d theta, and the d lambda, so that these, like this point is optimal. Okay, now I ensure that the equality constraints. How about the inequality constraints? It turns out that if the x lambda theta point is not degenerate, in other words, multipliers are not like the constraints that are satisfied with equality do not have 0 multipliers, then it turns out that the point that you will get from these equations will also satisfy the KKT inequalities as well. So the new point is indeed, the perturbed point is indeed optimal. Rearranging all these things, that they involve these gradients, but like G and F, I know the functions. I can take the gradients. It's nothing, super hard. So I can rearrange these equations and put them in a form like this, where I have some matrix S, dx, d lambda, and the d theta is on the right-hand side. Now, if you pick d theta to be, let's say, the first canonical vector, then you will get S inverse times the first column of U. That will be your partial derivative of X and lambda with respect to theta 1. How about the rest of the thetas? If you put an identity matrix for the theta instead of d theta, then the S inverse U will be the Jacobian of primal and dual variables with respect to theta. So here, this is the trick. This is not our theory. We are just applying it to the AC-OPF to get sensitivities of both primal and dual variables. But there is a caveat. S has to be invertible to do all this process. So when is S invertible? And what if it is not invertible? What do I do next? In general, if you see the general, optimization literature, people will say, well, in general, S is invertible. There are some weird points that it will not be, and we're fine. And usually that involves some second-order optimality conditions and the LICQ, linear independence constraint qualification. And usually in optimization, we take LICQ for granted, and we say it's typically okay. LICQ simply says that when you take all the constraints that are active and you take the gradients, then when you put all these gradients together, they should be linearly independent. Now, the caveat here and the interesting observation that we had, even when we solved the DC-OPF problem, we realized that the LICQ fails very often when you do the inverter dispatch. Even for the DC-OPF, it fails very easily. And we have a physical or intuitive interpretation for that in our paper in SmartGrid.com 2021. But so what do we do then? Does everything fail? Not really. We were able to show that although LICQ fails, and although matrix S is not invertible, still you can solve this system of equations with respect to dx, d theta. You will not be able to get this Jacobian because it doesn't exist, but you can get this Jacobian for most of the cases. So now, interestingly, we were able, in the new paper that we have put on archive, we were able to extend this result for the non-convex OPF, the AC-OPF. So we said our claim there is that under mild conditions, if this system is consistent, meaning if it has a solution, then the solution with respect to the dx is unique. Not the full solution is unique, but with respect to dx is fine. So the implication is that even when S is singular, the Jacobian that we are looking may still exist. There are some degenerate cases that it doesn't exist. For those cases, just drop those points. You can keep only the first part and do not do the sensitivity and form. Do not use the Jacobian to improve the DNN. Only for those weird points. Now, there is a quick slide here. It's a bit involved. I'll just give you the brief idea of it. So how do we? So we discussed how we can handle sensitivity analysis for differentiable problems, right? But that was my assumption. I could take Jacobian, partial derivatives. So the AC-OPF, we can formulate it as a QCQP, quadratically constrained quadratic program. Here V are the voltages. Complex here, they have been converted to real by expanding in 2. And here you see some quadratic functions, and that of course brings in the convexity that we all know. The non-convexity that we all know. And of course there are off-the-shelf solvers, QCQP solvers, local solvers, that they will give you local primal dual solutions. The good news, as I said, it is differentiable. The bad news, it's non-convex, so the solutions that you get may be locally optimal. But because it's differentiable, I can use the sensitivity analysis and get our claims, right? I can have like the formulas for the Jacobian. I know what the formulas look like. But I will not evaluate the formulas at the solution of the QCQP because it may be a local solution. What I will do is that I will solve the SDP relaxation, which means that I will make VV transpose and I will create a matrix V, and then I will have the trace, then all these quadratic equalities and inequalities become linear in capital V. Of course, I need this V to be rank 1, but the usual trick that we know is that we drop the rank constraint, cross our fingers, and at the end, V usually turns out to be rank 1, so the relaxation is exact, which means that we solved this original problem to optimality. And one would say, okay, why are you doing this back and forth between the two problems? Just do the SDP and go with that, which is globally optimal. My problem with SDP is that I don't really know how to differentiate through the SDP. I don't know how to take derivatives. There are some new works by Agraval, Boyd, and collaborators that they explain how to differentiate through the convex cone, but the analysis there, I would say, is a bit tedious. So we used this, let's say, shortcut, take the sensitivities from this symbolically as expressions, but evaluate them for the solutions of this problem. And you can show, it's pretty easy to see that the small v that you get from the SDP, the lambda and the mu, the Lagrange multipliers, are also KKT points of this problem. But now we know from this that they are also not only KKT points, but they are global, they are the global solutions. Something similar we can do with a MAT power solver, which is not a QCQP, but we can handle very similarly the sensitivities. And that's what we did here. We solved the AC-OPF with MAT power and on the 39 bus system. And here we get the mean square error, how it evolves with the training size. So the dotted, so the red is the plain DNN, the blue is our sensitivity SI-DNN. Okay, now when it comes to the dotted lines, that's during training. So when the training size increases, the training error increases as well, because you are trying to fit the same model to do good, to do well in many points, in more points. So the error increases. Of course, this is always the testing error. I'm sorry, this is the training error for the dot lines. For the testing error now, we have the solid lines, and you can see that as the training size increases, you train your DNN better, so it's more prepared to see other points, so the error decreases. But you see that the blue is consistently better than the red during testing, which is what matters. And one can say, well, these two lines are almost the same, they overlap. Like, what are you talking about? Big deal. Well, try to take this blue point and extrapolate, draw a horizontal line, and see that what the blue can do with just 10 OPFs during training, the red can do with 100 OPFs. So that's the advantage of these two curves. And this is, again, the same table as I had before. The idea is similar. The MSE decreases with the training size, and the SI-DNN does much better. And the same thing holds for larger systems, 118 and 200 bus system. You can see, let's say for this one, you can see that the MSE is half with 1/4 of the data. And how about time? The time does increase, but modestly. How about feasibility? I didn't talk about feasibility. Are these solutions feasible? And how about the SDP? So what you see on this slide is on the SDP results. And here you can see again the MSE of the two. The MSE again is improving much faster, right? And we have like 1/10 improvement. And here we have also violations. Violations in terms of constraints, and we normalize them in per unit depending on the, if it's a voltage, if it's a power or whatnot. So here you can see that the plain DNN has a maximum of 40% violation, and the SI-DNN has a 10% or 14, 15%, which is much better. We didn't do anything about feasibility. We have no guarantees. this is just numerical results. And this is how many violations we have per constraint. They are roughly 2 or 3 for both of them. The B column is the maximum violation. This is 0.5, this is 0.3. And this is the mean violation. This is 6, 7, 9, this is 1, 2, 3. So consistently, all these metrics show that the SI-DNN improves feasibility as well. How much time do we have? 5 minutes maybe, or 10?
I guess if you could finish in 5, 6, 7 minutes, that would be good.
Yeah. We can do it because now we have everything in place. So now we are switching to the OPF-and-learn setup. And let's see what is the idea here. OPF-and-learn. So now one can think of this of deciding the DER set points using or training control rules or policies. What is a rule or a policy? Think of the IEEE 1547 standard. It says that given V, you can control the reactive power by following this curve, right? So this is a function. Q says it's a function of V. It's a function of some parameters, of some inputs. These inputs here are local, but potentially they can be global. They can be the full theta if you want. So this is what we call a policy, right, or a control rule. Now, how do you design these curves? How do you design these slopes? You can do it in many different ways. One way to do it is through deep neural networks. And you can also make it more general, depending if you know like the full theta, then you can make the Q instead of V as a Q of theta. That looks like a DNN, right? So we migrate from the deterministic to a stochastic setup because now we have these policies, Q of theta, which before were trained for different points of theta, but we didn't have any claim in constraints, satisfying constraints. Here we can say that the Q of theta is a policy, and it has to be a good policy for a different variety of theta. So we have some PDF, let's say, of theta, and we do the expectation of the losses when it comes to DR control, and the expectation of voltages should be, the average value of the voltages should be okay. And also you can impose bounds of the DNN by using a tan H function. However, DNNs are hard to satisfy deterministic constraints, but at least by using this approach, we can ensure constraints on the average. So this is now what we call OPF-and-learn, because now the DNN appears inside the OPF. So this Q of theta is a DNN itself. So instead of optimizing over Q, now you have to optimize over weights. And you will get a policy where every time you get a theta, you see a theta, you will get a Q. And that policy is optimized in a stochastic way. So the good news about this is that we don't need labels. So we don't need step 1 of the previous process. We don't have to solve OPFs because now we are solving OPF while training. That's why we call it OPF-and-learn. We can satisfy stochastic constraints. Unfortunately, it's only stochastic, but there are some claims that we just adopt from this work. And also we can impose different DNN architecture constraints, structure due to communication constraints. So how do we do this? We take this problem and we apply stochastic primal dual updates. So here we have some Lagrange multipliers, and the W has to be updated using a stochastic descent. So the previous value minus the nu, and this is the gradient of the Lagrangian function. Losses and voltages, the derivatives with respect to the weights. And here we have also the updates for the multiplier, which should be updated like this. Now, how do we compute the gradients? We can apply chain rule. So for example, let's say you need the gradient of V with respect to W. You will do a gradient of voltage with respect to complex voltage times the gradient of complex voltage with respect to Q times the gradient of Q with respect to the weights. How do you compute all this? This one is backpropagation of the DNN. It's easy. This one, you can get it from the inverse function theorem because we know from the power flow equations, we know the gradients, we can invert it and get these metrics. And this is, again, the power flow equations, the definition of the voltage magnitude. We have some variations of this when you don't know the power flow equations, because you may have, let's say, a digital twin of the feeder, because let's say the utility, you are an aggregator, and the utility doesn't give you the full model. It just gives you a black box, which you can put Q and you can get V. So if you can do that, like these queries, then you can approximate the two first terms as one using finite differences. So these are some results. This is on the average losses. And what happens here is that we improve, this is a good policy in general. It's very close to the optimal policy. The good news is that the average voltage remains within limits. It's the blue curve here. This is the optimal, deterministically, on every instance. This is the average voltage, which is indeed within the range below the 3% that we wanted. But you can see very large fluctuations. Here is also the probability of voltage violation that we will see on the next slide. So how can we handle that? Essentially, we ensure that the voltage deviation, the average voltage is okay. But average voltage okay is not good, because there may be too high of voltages and too low of voltages at the same time, and the mean is okay. So how can we improve on this? We can do a non-convex chance constraint and say the probability of voltages being violated, voltage constraints being violated, is smaller than some alpha. This is non-convex, and we use standard tools from Nemirovsky and Sapiro that we can do a convex restriction of this. And here you see that, in fact, this is a restriction, as I said, it's a restriction, so you can get a more conservative results. So for example, here, this plot shows you per bus, these are the buses, and this is the probability of constraint of voltage violation. We asked for the violation to be less than 40%, and we get less than usually 10%. For this bus is 20% or 17%. Okay, these are some results on the gradient-free implementations. In general, I will not go through the test, but in general, they work, they operate well. We get a small disadvantage because you need more samples to get the same performance. And one last feature of these OPF-and-learn is that now we can answer the original question that we had. Can you solve an OPF with knowing only a few of the inputs? Or if the inputs to the problem are noisy, or you have a proxy. Let's say instead of knowing exactly what's happening in the grid, you just have a camera looking at the sky, so you can get some estimates of solar irradiance. Then here are the results that we get. This is when you have the blue, these are the voltage deviations, so the smaller the better. The blue is the full input, if you know exactly everything. These two are if you know at some buses, and this dotted is if you know the input only at the inverter buses, and you see of course, the deterioration in performance. And with that, I will conclude, and I will say that in this work we saw, we explored physics and aware deep learning solutions for the OPF. We saw two directions, OPF-then-learn, where we did sensitivity-informed learning to optimize. This uses existing OPF data and side information, and it improves on data efficiency at a modest increase in complexity. The other direction we explored is how you can take the DNNs and train them, not through a data fitting loss, but through the OPF itself. In this way, we can handle noisy and incomplete inputs. We can also handle communication constraints, which we didn't explore here, and which we didn't see today, and some open research directions, how you compute the proxy and the inputs, how you predict key variables, how do you close the loop when the DNN is fed with voltages that are they are affected by your decisions, and so on. And with that, I would like to acknowledge the great work of my collaborators, my two graduate research assistants, Manis and Sartak, Ming, who is also with Virginia Tech, and Professor Georgios Giannakis with the University of Minnesota, Guido and Andre with NREL. These are the works. The last one is in preparation, should be on archive next week. Thank you very much.
Great, thank you.
I'm sorry, I went a bit over time.
We still have time for a few questions. Anyone?
Maybe I can start with one.
Sure.
Can you hear me? Okay. Thank you so much, Vassilis. It was an amazing talk. I really enjoyed. It might be a naive question though. In the beginning of your talk, you said that we use DNN not for decision making, but for warm starting or preparing. I mean, some input data or removing some constraints. But I suppose at least in the first scheme, OPF-then-learning, the results you show us, for example, in page 9, they are the results of DNN, right? They are not some results that you got some results from DNN, then you put to DC-OPF or AC-OPF again and show the results. I mean, are they the direct outcomes of DNN or not? You use DNN for getting some warm starting and then solving the OPF problem again.
Yeah, thank you very much. Thank you very much for the comments and for bringing this up. Yeah, let me clarify that. Indeed, like all the results that I showed here was on what we got from like the raw output of the DNN.
So they are exactly the outcomes of DNN, not
correct.
Warm starting or I see.
Correct. Yeah. So these are the raw outputs. I just had that slide to say the possible uses. I agree that I didn't show those. I didn't like exhibit those uses in this presentation.
I see.
Why is that? Because when you do this like two-stage process, well, we haven't done that. We haven't explored that yet, because this is like a building. You know, it's like a first step. I should say, and we haven't done the second part yet. And it would be, it's a bit like it's kind of like hard to say if the, you know, when you have like the warm start and then you have something else that you warm started with, it really depends on what the second part is as well. And that would not be something that is ours.
I see.
So we want to see, you know,
just in the following my question. So it's a really amazing idea that you added sensitivity also when you train DNN. That's, I think, is real. But at the end of the day, still the quality of your results highly depend on your label data that you provide, the dots, the circles that you have. So I was wondering, is there any chance that we make, the DNN outcomes could be better than the quality of the input data we provide? Do we have any chance to improve the quality of our DNN better than the label data we provided? Let's say the quality of our label data is not good, and we are adding sensitivity, or is there any chance that we do a better job than the quality of than the label data we provided?
Yeah, I don't know. That's a very interesting question, yeah. And perhaps some avenues, but we have some very rough ideas in that direction. When you have like stochasticity in the inputs, some ideas that we have is somehow to use the tool of GANs, generative adversarial networks, where you know, you train a neural net with some random inputs and somehow incorporate that. We have not considered that yet. We have written some proposals, but that's how far we have gone.
Thanks a lot, Vassilis, again. Very amazing.
Thank you.
Okay, so we have another question here, Jose.
Hi, thanks for the talk. Can you comment a little bit on the architecture you used to train these DNNs?
Yeah, so for this one, I have to check my cheat sheet here. I believe, I cannot recall it. I believe it's 3 layers and each one of them may have 10 neurons. I cannot recall. And also it depends on the application. Let me check here. I can check on my, I have to exit this. I have to exit on the, I cannot recall, to be honest. But we have it on the paper. I believe it's the 3 or 4 layers.
Okay, that's okay. I was just wondering, like, there are like so many advances, right, in the architecture search or architecture design, and I wanted to have like a rough idea of what kind of network can represent OPF, right? And it's actually good results that simple networks like just feed forward, right? nothing fancy like transformers or CNNs can represent OPF. And I just follow-up comment on the previous question. That will be actually really interesting. Like if you feed the network, say DC OPF solutions, and it may at some point with architecture search or something or GANs can generate somewhat similar to an AC-OPF feasible solution. That would be amazing. Just a comment on that. Thank you for the talk again.
Thank you, thank you. I'm sorry I don't have the details.
Right, that's Dong Chen.
I also had a question on the scalability. So I guess for small scale systems, it's already like pretty easy to solve with like local search algorithm, but I guess it would be beneficial for like large scale optimization problem. Then you think like there will be also like trade-off between the amount of training data you would need as you grow up the scales. So yeah, would you have any comment on that?
Yeah, that's a very good question. Here we went up to 200, which is, it's large, but it's not, it's far away from the MISO, what MISO is solving that has, 40,000 buses. And that's a good question indeed. How things can be scaled up and also where to sample in the OPF space. Perhaps if you have all the OPF decisions from the past, you can use that. So, the step number one, it's kind of like already there for you. Of course, you may have like different topologies and things like that. We don't really exactly know how to sample thetas so that they are reasonable. That's kind of like an active learning problem. And also, I would say that perhaps things may not scale well when you have many, like the DNN is predicting many decisions. However, as I said, it can be useful even for big networks if you are trying to predict like tie lines. Like let's say the line flow on 10 tie lines between, let's say, PJM, MISO, and NISO. Maybe there are like 20 variables to predict. So then you don't really care about the full X, but you have like a subset of X. Or perhaps you care only about a few lambdas. And if you know those lambdas, then you can do dual decomposition of the big OPF and split it into smaller areas, which are much faster. These are just some ideas. I have not addressed your comment to its core. It's a problem that exists, but these are some ideas that can somehow go in the direction that you are thinking.
Right, so we are well past the hour. Last call for questions.
If there is no question, I can ask more, but I know I already asked one. So.
I see no raised hands here. So, okay, so you get the last question, Dalal.
Thank you. So this result, exactly the results of this slide. If we go for a network system more under stress, with more constraints binding, more, transmission constraints binding, can we expect to have more MSE or not? I mean, have you tried to test your system under different networks with congestion, without congestion, to see what's going on?
That's a good idea. So we tried these three networks, I guess, on the nominal, on the benchmark. Oh, of course, what we did is that we did like the loads were changing. And now I'm not sure if we did not.
Because you had a plot with the number of infeasibility instances. So I was wondering if you go for, yeah, exactly this one. So if you go for a network which is more under stress, can we expect to have more instances or not? Maybe yes, I don't know.
So yeah, so this, what was happening here, like what we saw here, so this is the constraint violation. So it should be 0 for everyone. And this means that the decision that we got from the PDNN or the SI-DNN was not satisfying that constraint by this much. And this is significant, both of them, at least 10%. So this doesn't show how many of the original constraints were binding. You're right. So we haven't done any study on that, but our results are, we did vary the loads. Now, of course, by how much you are varying the loads, you can create more or less congestion. We didn't play with that.
Yeah.
But it's good to see it. We will see it.
Thank you. Thank you, Vassilis.
Thanks.
Interesting direction for future work. So yeah, thank you very much, Vassilis. Very fascinating talk. So thank you once again. And to all of you, we will continue the seminar series in 2 weeks from now. Kyrie Baker from University of Colorado. Hope to see you all again then, and feel free to tell your friends and colleagues about this series as well. Thank you.
Thank you very much.